Hello guys, welcome back to Thermogeosphere. Today I'll be interacting with you on a very important topic from the geomorphology section, that is isostasy. I somehow find that students always coming back to me for more clarity on the concept of isostasy. I don't know, for some reason there always remains some confusion in the minds of the students. I'll try to simplify it and make you understand in simpler terms the concept of isostasy, which is one of the most fascinating subjects in the evolution of the Earth's crust. So let's break that word isostasy into two. Isos means basically same, and status means standstill or a steady state. So in other words, isostasy means a kind of a gravitational equilibrium between the brittle lithosphere and the solid asthenosphere. It's solid, but it's like paste, it is mobile. So, and this gravitational equilibrium between the lithosphere and the asthenosphere enables the plates which lie on them to just float around and move about. So, simply speaking, you can also say that isostasy is just the lighter crust lying above the underlying dense mantle. So, though waning ice sheets, sedimentation, volcanism and all disturb this equilibrium, the magnetic studies and the gravity studies have shown that the outer layer somehow managed to keep the equilibrium intact. So we will understand the historical context of how the concept of isostasy evolved, and then we will see what are the types of isostasy, and then we will see the various hypotheses put forward by Airy, Pratt, Minsas and Heiskanen. These four are important hypotheses put forward for understanding the concept of isostasy, and then we will also go on to see the application of isostasy in various geodynamic models, and then we will conclude. So stay tuned. I will show you simple, very clearly understanding slides, like how you have a spring bed on which a very heavy weight person can sleep. The springs of the bed somehow manage to take that kind of a weight. In a similar way, or in similar analogy, the lower mantle, underlying mantle, can take the weight of the Earth's crust, which has huge mountains. They are very high, but the height of the mountains is quite equivalent to the depth of the mountains in the Earth's crust. So I'll try to explain, and the basic principle behind the isostasy is the Archimedes principle, which you may have studied in school, that you can straight away apply to this, and you can more easily understand the concept of isostasy. So, is the person resting on top of a spring mattress in a state of isostatic equilibrium? Yes. Because like the springs inside the mattress, the elastic lithosphere can also support excessive mass like the mountains or the plateaus. Thick plates can support more excess mass than the thin plates, obviously. So this is the example from the Hawaiian chain. It has two effects. One is the elastic flexure due to the island load. This flexure hypothesis was put forward by Minsas. And then a swell due to mantle upwelling. You can see the graph here. So isostasy, as I said, is derived from two Greek words, isos and status. Isos means same and status means standstill. It refers to the state of gravitational equilibrium between the Earth's lithosphere and the asthenosphere, such that the tectonic plates easily float. And in its simplest form, isostasy views that the lighter crust is floating on the dense underlying mantle. So, though the waxing and waning of ice sheets, sedimentation and volcanism disturb the isostasy, and some cases prevent equilibrium from being achieved, but the seismic and gravity data suggest that the Earth's outermost layers generally adjust to these disturbances, and more or less and by and far the equilibrium is maintained. So the discovery that the Earth's crust might be in a state of isostatic equilibrium is one of the most fascinating stories in the history of science. So when attempting to study the isostasy, the first scientific principle one needs to know is the Archimedes principle, which states that as an object is partially submerged in a fluid, the weight of the fluid that is displaced is equal to the weight reduction of that object. And this concept can straight away be applied to the Earth. The asthenosphere acts as a fluid and lithosphere as a rigid that floats on top. And then this is the lithosphere versus asthenosphere. The upper mantle is composed of two parts. One is the lithosphere, which is all solid, and then the asthenosphere, which is a plastic layer, just like a paste, which is solid but is mobile. You can also use the deflection of the plumb mob near the mountain change, which shows the calculations show that the actual deflection may be explained if the excess mass is cancelled by an equal mass deficiency at greater depths. Then history, the expeditions over Andes led by Vogler, a French scientist who studied isostasy for the first time, and a century later similar discrepancies were observed by George Everest, a Surveyor General of India, in surveys south of the Himalayas, indicating a lack of compensating mass beneath the visible mountain ranges. The general term isostasy was of course coined in 1889 by the American geologist Dutton. So isostasy is a term, as I said, derived from iso and status, meaning equal standing. Steers later in 1961 said this doctrine that wherever equilibrium exists on the Earth's surface, equal mass must underlie equal surface areas. Then isostasy can be local and also regional. According to Pratt and Airy, excess mass is perfectly compensated everywhere. This is the situation of local isostasy, but when you come to regional isostasy, the situation is where some of the load is supported by the strength of the lithosphere. So this is normally called as the regional isostasy. Then the hypothesis of isostasy, Pratt and Airy, you just try to, if there is a question on isostasy in general, try to compare Pratt and Airy, because these are quite old hypotheses. But if they say Airy's hypothesis of isostasy or Pratt's, then you will have to write in detail, which I have given you in these slides. But otherwise you can just compare and then write about Menes and Heiskanen. The Pratt Airy's isostasy says that the mountain range is supported by changes in the crustal thickness, crustal density relatively constant. And whereas the Pratt says the mountain range is supported by density variations within the crust. So either way, the plate is relatively light and floats on the fluid layer lying beneath it. This is the concept of George Airy. Airy's hypothesis says that the rigid upper layer and substrate are assumed to have constant density. The isostatic compensation is achieved by the deep roots or the iceberg-like things below it. There has also been criticism of the Airy's hypothesis, which says the principle of flotation results in 1:9 ratio of fraction above surface is to be submerged. But in this manner, Himalayas will have about 85 kilometers of root. But this can't be the case, as such depth of cealic material, once it goes down the depths, it will, because of the heat, will melt away. Then the concept of Pratt, he says depth of base of the upper level layer is constant, and the isostatic equilibrium is achieved by composing the upper layer of columns of constant density. The Airy said that of different densities, whereas Pratt said it is of a constant density. So Pratt's hypothesis also has been criticized for his principle of flotation like Airy, and also the phenomena of root formation in impact series like Airy's, and that was also criticized on the same grounds. So the fundamental difference between Airy's and Pratt's view is that the former postulated a uniform density with varying thickness, and the later as uniform depth with varying density. So one is varying thickness, that is Airy, and the other is varying density. That's how the moot point, core point is that, and remember, and then draw these two diagrams, and that will be done as far as Airy and Pratt are concerned. Coming to means, Menesh is as they is pronounced, or the flexural isostasy model, where the lithosphere acts as an elastic plate and its inherent rigidity distributes local topographic loads over a broad region by bending. So this hypothesis was suggested to explain how large topographic loads such as the sea mounts, example the Hawaiian Islands, could be compensated by regional rather than local displacements of lithosphere. So this is the more general solution for the lithospheric flexure as it approaches the locally compensated models above as load becomes much larger than the flexural wavelength, or the flexural rigidity of the lithosphere approaches zero. So this is the regional or Venning isostasy. The lithosphere flexes under its own weight and shields the asthenosphere from the differences in the pressure. The Heiskanen hypothesis was developed by a Finnish scientist. He tried to bridge the concepts of Airy and Pratt and brought in an intermediate or a compromise hypothesis. This hypothesis says that approximately 2/3 of the topography is compensated by the root formation, that is the Airy model, and 1/3 of the Earth's crust above the boundary between the crust and the substratum. So he included both the concepts of Airy and Pratt and developed a composite model. According to Heiskanen, larger the C-Alex section, deeper will be the root, larger the section, lesser will be the density, and density slowly increases with depth. Quite recently, as I said, the fundamental concept of Airy and the Airy continental masses floating on the CL blocks in a heavier substratum was rejuvenated and brought back by the influence of Heiskanen's work, so that now it's more probably true to say that most geographers and geologists favor Airy's explanation. But don't go overboard, don't write too much about Airy or Pratt, just balance it out and bring in Mensch and Heiskanen, and then try to end it. So applications of isostasy suggest that the Earth's crust should adjust to any changes in mass that occur at the Earth's surface, called the isostatic adjustments. So these are basically two types of responses to isostasy. One is the subsidence and the other is the rebound. The example for subsidence is the advance of glacial ice sheets, that is waning of and waxing of the ice sheets in the Earth's crust, and the rebound is the post-glacial rebound, as you can notice in the Scandinavian ice sheets in the United States. It should be noted, however, that isostasy explains why continental plates cannot be subducted, because the forces that drive subduction cannot overcome the buoyancy of these low density plates compared to the highly dense plates of the oceans. So this is how what explains the post-glacial rebound in a very simple diagrammatic way. So that's all, guys. More than anything else, try to understand the concept of isostasy, write one or two paras about what you have understood in isostasy, give an analogy and example, but try to remember the four hypotheses of Airy, Pratt, Menes, and Heiskanen. So that's all, guys, as far as isostasy is concerned. We'll catch up with two more small topics, that is the principles of geomagnetism and the physical conditions of the Earth's interior. Both I will be taking in the next few classes. And so stay safe, stay focused, study well, and all the best. Bye.